Okay, so in this video, we are going to go through this question from CJC H2 Math, 2023 Prelim Paper 2. So question 8, we have this store that keeps a bin of large number of oranges. It is known that on average, P% of the oranges are rotten. The oranges are packed into packets of 10 oranges each, and the number of rotten oranges in each packet is denoted by the random variable x. State in context two assumptions needed to be well modeled by a binomial distribution. Okay, so whenever you're asked to state the assumptions in order for something to be modeled by a binomial distribution, how I remember is using this. So recall, let's say I write down a binomial distribution. Typically speaking, I'll write down something like x is binomially distributed. Okay, n number of trials, probability of p. Right. So let's describe each of these parts. Right. There's three things you can learn from here: b, n, and p. Okay. B means binomial. And what does binomial mean? Bi means two. Binomial suggests that you have two outcomes. In fact, it should be two mutually exclusive outcomes. Okay, now next one, n. N talks about the number of trials, right? So n is the number of trials, yes, but n is the number of independent trials. So we want to be a bit more specific about what trials we are talking about. In this case, they must be independent. The probability of the event of one orange being rotten should not affect the other oranges in the same packet, for example. The third part that we can talk about is the probability, P. In this case, it should be a constant probability. A constant probability of whatever outcome it is, because binomial distributions, you only have two mutually exclusive outcomes. So it's constant probability for technically the success and therefore also the other outcome. Okay, so these three letters here will give you three different assumptions that you need to make. In this question, let's make two assumptions, and let's say the first one, we are going to talk about the independent trials. That's typically the one that I think is easiest to write about. Okay, so first one, okay, we want to talk about the independent trials, but we want to fit it into context and be a bit more specific about what we mean by n independent trials. So for example, the event that an orange is rotten, okay, in this case is a packet of 10, right? So in the packet of 10, okay, is independent of the other oranges, okay, independent of the event that any other orange in the packet is rotten. Okay, so we just want to fit into context. So just tell them what it means to be independent trials in the context of these oranges in packets. Okay, and we just want to sneak in the number of trials, right? Okay, so one thing to take note here is just a point about how we phrase things, or how the words in this context work, right? So what I want you to take note is that only events, okay, only events can be independent. You cannot say things like probability is independent, right? So probabilities cannot be independent. Okay, there's no such thing. Probability is just like chance, right? The chance of getting something is not independent, it's the event that's independent. Okay, so it's just a little bit of semantics lah. Okay, next one. So we had one assumption stated already. The other assumption, we can say the probability. So because they said that on average, right, it is known that on average P% of the oranges are rotten. So that doesn't really mean anything about the probability of each orange. So this is the assumption that we want to make. We want to make an assumption that the probability, okay, the probability that each orange is rotten, okay, is constant, because constant probability, constant at P%. Okay, so we want to tell them, we want to basically sneak in some of the keywords, basically constant, the probability is constant, okay, it's for each one, okay, each orange. Okay, this is just to fit into context. In the above assumption just now, we want to talk about how the events are independent to the event that other ones are rotten. We want to also sneak in the 10 trials. Okay, so part A is done. Okay, let's look at part B. So part B, assume now that X follows a binomial distribution. Okay, so it is given that P equals to 20, and we have, okay, let's just write down first. We have X is binomially distributed. There are 10 oranges in a packet. The probability that an orange is rotten is 20. Okay, P equals 20, 20%, so 0.2. Okay, I'll just write 0.2 because it's a bit neater than 20%. Okay. Now we want to find the probability that there are at least 2 rotten oranges. Okay, so probability that there are at least 2 rotten oranges in a randomly chosen packet. So more than equals to 2, we, on your GC, you can't really ask your GC about what is the probability of something more than or equals to 2 for binomial distribution. So what you should do is you should write it as 1 minus the probability of some other stuff. So the question now is 1 minus what, right? So some of you might have memorized it, but I think it's good to have a contingency plan on how to visualize or how to derive it on the spot. So let's say I have a number line here, and this number line tells me the number, like all possible numbers of rotten oranges in a packet. So this is the X number line. Okay, X can take up certain values, like let's say 0. Let's say 0 has this probability. This is not accurate. I'll just anyhow draw some rectangles. But for 0, I have some probability. For 1, I have some probability. For 2, I have some probability. And then I have 3, 4, and so on and so forth until 10. Okay, so whatever, I don't really care. But I have some probabilities, right? And I want to find the probability that X is more than equals to 2. So I actually want here, okay, including here. I mean, this is bar chart, right? So I can just cut off here and include everything here. All the area of these bars on the right hand side. Okay, I want all the way until the kind of like positive infinity. But in this case, it's just up to 10. Because 11 onwards, there's nothing. Okay, so I want all these probability. how can I describe all this probability? What I can do is I can take all the probability, which is 1, minus everything on the left side, which is up to x equals to 1. In fact, we can just have these two probabilities. So this this green color part, what we can find using binomial CDF, right? So we need to always think about how can we ask our calculator. We can use binomial CDF for probability of x less than equals to 1. CDF, the C stands for cumulative, right? So you accumulate up to 1. Everything that is up to 1. So 0 and 1. Another way is to use binomial PDF, which tells you the probability at each value. So you can ask your calculator what is the probability when x equals 0, what is the probability when x equals to 1. Okay, so anyway, there's only 2 values, so you can exhaust 2 of them, not too difficult. So the idea is I want the red color part. I know the whole probability is 1 whole. Okay, if I can minus this green color part, because I can find this green color part, if I subtract this, I will get the red color part I'm interested in. So this will be 1 minus probability of x up to 1. Okay. Now, what do you type in your calculator? What you should type is, this is 1 minus binomial CDF. This is up to 1, right? So binomial CDF, accumulate up to 1. Okay. And then you should put in 10 trials, probability 0.2. You want up to 1. This is what you type into your GC. And your answer should come out as 0.62419 ... and then you can round off to 0.624. And that is your answer. Okay. Okay, so next one, part 2. In part 2, they say that 100 packets of oranges are sold at a profit of $2 per packet. The store offers a discount, okay, whenever they discover a rotten packet. Whenever they discover any packet containing more than 1 rotten orange. In fact, contains more than 1 rotten orange, that just means more than equals to 2, right? Because more than 1 must be 2 onwards if you're talking about integers. Okay, so by finding the expected number of packets of oranges that contains more than 1 rotten orange, right? Find the range of values of D if they want to expect a net profit. Okay, let's take it step by step. Finding the expected number of whatever, this is step 1. Okay, we want to find this first. Then I want to find the range of values of D if they expect a net profit. This whole thing is step 2. Let's focus on step 1 first. So we have 100 packets. Okay, 100 packets. We want to find the expected number of packets that contain more than 1 rotten orange. So for part 2, okay, let's denote a new variable. Let's write y. Let it denote the number of packets of oranges. Okay, packets of oranges that contain more than 1 rotten orange. 1 rotten orange. Okay, out of 100. Okay, so out of 100. So in this case, okay, y is the number of packets that contain more than 1 rotten orange. This is binomially distributed. It has 100 trials. The probability is exactly what we found. Probability that x is more than equals to 2. Okay, this is from part 1, sorry. B part 1. Okay, now what is the expected value? They gave us a clue, right? So expected value of this is just NP. So N, which is 100, times P, which is probability of X more than equals to 2. This is the expected value. You can find out the answer if you want to, but I'm just going to leave it like this first. Okay, they didn't really ask us to find the expected number of oranges. They just said by using that, we want to find the range of values of D to expect a net profit. Okay, what does it mean to expect a net profit? Okay, actually, you know what? Let me just write down the answer here. Anyway, it's just this number times 100. So I will just write down that this is equals to, so whatever I wrote here, right? Okay, I just gonna times 100. So I have 62.419 ... and I round off to 62.4 3SF. Okay, actually, you know what? Just leave it like this lah. You can write down the 3SF. It's not very important. It's not a marking point. Okay, but I just need this for later on. Okay, now next one. Let's try to understand how this works first. They mentioned that if I sell 100 packets and each packet, no issue, I sell it at $2, profit of $2 per packet, which means if no, I'm just gonna call it bad now. Okay, so if no bad packets, then the profit should be $2 times 100 packets, $200. However, for every bad packet, we discount D dollars. Basically, we lose D dollars per bad packet. Okay, per bad packet. So now the idea is, how many bad packets do we expect? We expect 100 times this probability, this number of bad packets. Okay, this number of bad packets. Okay, so let me just write down here. This is the expected number of bad packets. Okay, now that we have the expected number of bad packets, we lose D dollars per bad packet, which means the net profit, which is equals to $200 minus this expected or expectation value. Okay, so minus 100 times probability of X more than equals to 2 times D. Okay, because that's the amount of money we lose per bad packet. This is the expected number of bad packets. This is the net profit, and I want to earn money, right? I want to earn money. So I want my net profit to be positive. Okay, now they want us to solve for D. Okay, so to solve for D, let's bring this whole thing over. Okay, so 200 is more than 100 times probability of X more than equals to 2 times D. And then D, I want D, so I divide by these things down here. These are positive values, so there's no issue when I divide it over. I'm going to divide over and I'm going to flip the inequalities to this direction. Okay, so 200 over 100 probability of X more than equals to 2. You can simplify this fraction if you want to, like the 200 over 100, but your calculator should know how to deal with this. And this should give you, a 3.20 something. Okay. Answer. Okay, anyway, we have exact value. So I'm just going to write this is 3.20 to 2dp. And the reason why I want 2dp, sorry, let me plug in my iPad. The reason why I want 2dp is simply because I have, it's simply because D is in dollars, so dollars and cents. So actually 2dp is like to the nearest cent. Okay, so you can say is to nearest cent. Nearest cent. Okay. Alright, let me shift things around because I don't want to add a new page. Okay. Okay, so like this. Now, I have this inequality here. D is less than this. But D is a discount, right? It's a discount. So a discount or the discount value should never be less than 0, right? So discount value should be more than 0, which means my range of values of D would be 0 up to 3.2 or $3.20. This is my inequality. Okay, so part B part 2 is done. Let's look at part C, sorry. Let's look at part C. For part C, the store manager wants to ensure that 95% of the packets of oranges contain at most one rotten orange. So basically, I want to ensure that 95% of the packets contain at most, okay, packets, right? So packets will be X, right? So X is the number of rotten oranges in one packet. I want probability that the packet has at most one. At most one just means one or smaller. Probability of up to 1. I want this to be 95% because I want to ensure that if I have many packets, only 95% of them, or I want to ensure that 95% of them contain at most one rotten orange. I want to write down an equation satisfied by P, and in this case we are assuming that P does not equals to 20. Okay, so how to know this? Even though they say P equals to 20, P equals to 20 is not in the preamble. It's in the part B. That means if we move on to part C, P equals to 20 doesn't make sense anymore. It doesn't apply anymore, right? So even if we don't know this or we didn't pay attention to this, if I want to find the value of P, then P must be an unknown. Can't be a 20 or something. So I have this equation that I want to set up. But before I set up this equation, I need to remind myself that X, okay, is binomially distributed. There are 10 trials and P percent or P over 100. Okay, that's the probability that an orange is rotten. Okay, so now I have probability of X less than equals to 1. Probability of X less than equals to 1, well, I can just write it as probability of X equals to 0 plus probability of X equals to 1. This is equals to 0.95. Okay. So up to here, actually, you know what? Since they say write an equation, so I should probably write this out first before I type into GC. But if they didn't say this, so if no equation is required, okay, just use GC here. Okay, just use GC here. The idea is I'm going to plot this as y1, plot the other side as y2, then just see where it intersects. We let P be the variable X in our GC. But in this case, we want to write down an equation. So let's write it like this first. We want to write this probability in terms of numbers, right? I don't want this probability, whatever this thing is. So probability where X equals to 0, when this is a binomial distribution, then the probability that X equals to some number, okay, so recall from MF26, okay, from MF26, okay, that let's say I want let's say I have a distribution X is binomially distributed with NP, then the probability that X equals to small x, for example, this is equals to n choose small x times probability of the success to the power of x, because I have x successes, multiplied by the probability of failure, so 1 minus p to the power of n minus x, because I have x successes, there are n trials in total, so n minus x left. So I have this formula here, right? I have this equation here. What I can do is I can write this, just the small x is 0, small x is 1. I can write it in this form. So let's write it out. This is 10 choose 0 times p over 100 to the power of 0 times 1 minus p over, okay, let's write it as one fraction. 100 over p, 100 minus p over 100 to the power of 10. 100 minus p over 100 is just because 1 whole minus p over 100. That's just the probability of failure. Okay, plus 10 choose 1 times probability of success, or p over 100, to the power of 1, and then the probability of success, so 100 minus p over 100 to the power of 9, which is 10 minus 1. And I want this to be equal to 0.95. Okay, from here, if you want to, you can simplify a little bit. First of all, 10 choose 0 is 1, 10 choose 1 is 1. Next thing is, this whole thing is equals to 1. Next thing is, there are 10 hundreds in the denominator here, 1 plus 9 hundreds in the denominator here. I will cancel all of them by multiplying both sides by 100 to the power of 10. 100 to the power of 10. And now my answer, or rather my left hand side, would be 100 minus p to the power of 10 plus, okay, I need to multiply everywhere, so 100 to the power of 10 as well. Okay. Actually, you know, don't need, actually, sorry. Let me reverse this. I don't need to do that because I can just use GC from now on. Anyway, I have formed the equation, so I can just write down in GC. But of course, let me just still clean up these parts where are equal to 1. Okay, so I'm gonna write it like this. Sorry, should be in red. 100 minus p over 100 to the power of 10 plus p over 100. Okay, p over 100. Okay, 100. And then times 100 minus p to the power of 9. And then the 100 below is to the power of 10. Okay, so I have this. If you want to, you can also split this into power of 10, power of 10. Okay, power of 10. Okay, then we have equals to 0.95. If you want to, we can do it what I did just now, to multiply by 100 to the power of 10 on both sides. If not, you key this as y1 in your GC. Key this as y2 in your GC. Okay, so using GC, okay, using GC, comma. Now, GC, when we do this kind of like equations or inequalities, right? GC can help us by, or we can look at the graph or look at the table. To decide which one to use is to look at P, the variable we are solving for, the unknown we are solving for. P is continuous. It's not just whole numbers, it's not integers. So for P, I should use graph. Okay, using GC graph. I will just briefly sketch it out. Okay, I'll briefly sketch it out. This will look like this. Okay, actually no axis. You know what, I'll just draw it like this. Okay, so okay, Yeah, okay, correct. So the x-axis is quite low, but well, okay, never mind. I'll just draw it like this lah. Okay, you don't have to finish drawing this. The important part is where they intersect. So let's label these two graphs. This is y2. Y2 is 0.95. Now the other one is y1, and y1 is 100 minus, in this case in a GC is x. If you want to write p, as you also can write p, but I prefer to write what I see on the GC. It's 100 minus x to the power of 10 plus x times 100 minus x to the power of 9 whole thing over 100 to the power of 10. Okay, so I have x, origin, y, things like that. So now we just need to look at what this intersection is. At this intersection, that will be the P, right? So from our GC, if we look at what the value of this number P is, or this probability is, P is equals to 3.677143.8. Okay, whatever that is. Okay, so we get this value for P. P is a probability, so we just round off to 3SF, 3.868. And we are done. Okay, so just to recall, okay, before we end this video, whenever we use GC, okay, use GC to solve equations or inequalities. Okay, so the idea is like this. If we are solving for discrete integer values, okay, then we use table. Okay, use table. If we are looking at continuous values, then we look at graph. Okay, so for table, it will be things like, let's say, number of trials. That will be discrete. That will be integer values. In that case, we should use table, because table, when we look at table, the n, or the x value, right, would be discrete. It will be integer values, which means if I'm looking for an integer value, I can simply look for which row, which x value gives us the desired or satisfies this equation, for example. Okay, but for graphs there will be decimals most of the time. Okay, and if I want to look for a whole number and I look at graph, then I will have to think about, should I round up, should I round down? How do I make that decision? That's a little bit more complicated than needed. So what we should do is if we have integer values, we look at table. If we want to look at the value of an unknown that is continuous, then we look at graph, like in this case. Okay, so that's all for this video.